Today we're simulating falling sand in a two-dimensional grid. So the sand always starts at position 500, 0, and then falls down, and the exact rules for falling down and settling will be explained later. Our puzzle input are these line segments of rocks. For example, this line segment consists of 3 points, 1, 2, 3, and our inputs here are the points 1, 2, 3, and similar for the other line segment here. Okay, so of course, first of all, we have to parse this string into the line segments. So we start by splitting with new line as usual. Then we have individual text lines. And then we reseek for number, comma, number. That should give us all the points as sequences. And then we map the parseLong function over that as usual. So map the parseLong will give us 1 point. Then the inner for will give us a line segment, and the outer for will give us all the line segments. Right, and I represent this grid as a one-dimensional Boolean array. And this function shall draw a line in this Boolean array from x1, y1 to x2, y2. So first of all, I calculate the direction vectors, dx, dy. For vertical walls, dx will be 0, and for horizontal walls, dy will be 0, and the other one will be -1 or +1. I simply subtract and then call the integer signum function. That's a quite useful function since 2004, and I always tend to forget that it exists. Right, then we start at the starting point, point 1. We set the value in the appropriate position to true in our array. So this just converts a two-dimensional coordinate into a one-dimensional coordinate. It's just a 1000 by 1000 array, if you will. Okay, and after that we check, have we already reached our destination? If we have not reached our destination, then we recur with updated x and y values, just by adding the directions onto them. Right. And then our makeGrid function creates this Boolean array from the paths that parse paths spat out. So here we create the array of 1,000,000 elements. Here we loop through all the paths, and then every path is partitioned. We already know this function. Why do we need to partition with 2, 1? Because this is one line, and then this is one line, right? So this point is shared between the two lines. That's why we move this window over it. Okay, then we have our line. We draw that line, and then we're done, and we can return the grid. Right, then we have a function that attempts to drop another grain onto the grid. So here's our grid again. We start at position 500. That's, well, first line and then in the middle of the line. And then we compute 3 positions under us. Directly under us is 1,000 more. 1 to the left under us is 1 less than under us. And 1 down right would be 1 more than just down. And then, there's some conditions to check to see how to proceed with the sand. So if we have already left our grid, then we return false. This means the grain fell into the abyss below. If the grid immediately below us is false, so it isn't occupied, it is free, that looks like this, here's our sand and here is free, then we can simply fall down. So we will just fall down. Otherwise, below us is already blocked, either by sand or rock, but if the left is free, which is checked here, then we can recur to the left. Otherwise, both down and left are occupied, but if the right is free, which we check here, then we can recur to the right. Okay, and otherwise all 3 positions below us are already blocked, so the sand will stop here. So we simply put it into our array or mark it as true. Right, and then for part 1, how many units of sand come to rest before sand starts flowing into the abyss below? We parse our paths, we make the grid, and then we start counting at 0. If we could drop another grain, then we increment the counter and try again. Otherwise, the counter holds our final result, 24 in our example. So that's quite easy once everything else is set up. Then for part 2, there is no more abyss below. Now there is a floor, but we have to determine where it is. So we shall find the highest y coordinate in our input and then just add 2. Okay, so we loop through all the paths again, destructure all the points on those paths, look at the y coordinate, reduce with maximum starting at 0, and at the end add 2 as required. Okay, and then we return a line from 0 to 999, so the complete extent at the calculated y position. Right, and then for part 2, which took quite a long time to run, about half a minute, the LED bindings are the same except for this additional LED binding. So we find the floor, which is another line, and we const that line onto our paths, so it will also be painted or drawn by make grid. Okay, then we start counting at 0 again, check if the source is already blocked. If it is blocked, then we are done counting. Then we have our result 93. Otherwise, we drop another grain, increment the counter, and try again. So also not that hard, but unfortunately quite slow. But still manageable, about half a minute. Right, and then I got a bit curious, can this be done faster? And I browsed Reddit for a bit and I found a really cool solution. So here's the basic intuition. If you look at the end result of filling our world with sand, then the word fill already hints at, maybe we can do that with a flood fill, a breadth first search. And indeed, we can simply start out here, and then how do we explore? From here, we explore all 3 neighbors to the south. And from each of those neighbors, again, we explore the 3 neighbors to the south, which will, of course, result in some overlap, which we have to get rid of. But it's quite simple. We never go horizontal or up, only down. Right, and that made it much faster, only about 200 milliseconds on my computer. So let's see what happens here exactly. So now exactly the same LED bindings as before, the same counter, but now I have another binding here for my loop. Which grains am I currently looking at the current line? So 500 is this guy, right? And the current line at position 500, there's a single grain. And then we count how many grains are there. That would be 1 initially. If the count is 0, then we are done. That would be here if we reach the bottom. Otherwise, we recur. We add the end to our counter. And then we want to process the grains into a new empty vector. How do we process them? We process them in 3 steps. The first step is a mapcat, which is called flat map in other functional languages. So for every grain, we compute 3 new positions, down left, down, and down right. So we expand 1 grain into 3, if you will. And that can produce some overlap, as we saw here, right? There were lots of overlap here. And we can get rid of the overlap with the distinct transducer, which internally just uses a simple hash set, apparently. Okay, and then the usual remove function. We check every grain, what the value in the grid is, and if it is already true, then we remove it, because we don't want to explore, for example, these guys. We have to remove them, otherwise we would fill literally everything and we would just have a large triangle. Okay. Yeah, and that's already all, and that ran quite much faster, about 2 orders of magnitude faster.